Okay, in this podcast we're going to talk about photoelectron spectroscopy and explore what we know about the atom based on it. You know, I like to think about these notes as really looking at how we know what we know about the atom. Okay, so we're going to, as an overview, we're going to take a look at the data that have led to lots of revisions of the atomic model. We're going to investigate the basic setup of photoelectron spectroscopy, the instrument itself. We're going to explore what it's able to tell us about the atom, and then we're going to explore some PES data. So the first thing I'd like you to do is pause the podcast and answer this question. See if you can match the experiment to the model. Okay. All right, welcome back. So if we take a look at these, the first model, the basic model of the atom came from Dalton, where he did a lot of experimental work looking at how atoms combined to make molecules, and he discovered that atoms combine in simple whole number ratios, and that he said there was nothing smaller than the atom. And then along came Thomson, who worked with the cathode rays in the cathode ray tube, and he noticed that when a magnetic field was applied, that the ray bent towards the positive plate, indicating to him that there must be something in that atom that was negatively charged. He called those corpuscles. We call them electrons now. But also knowing that the atom was neutral, he reasoned that there was some goo in there that must be positively charged, and he came up with a plum pudding model. But really our first model that included some particle that was smaller than the atom. And then, of course, came Rutherford, who was Thomson's student, who took alpha particles and sent them through a tiny gold leaf, expecting that they would go straight through if you had this plum pudding model, but discovered that there's something that very rarely causes these beams to deflect, leading him to believe that there's a very dense, positively charged center of the atom. And so he discovered the nucleus. Okay. And then, of course, Bohr was trying to explain the emission spectrum of the hydrogen atom, and came with the idea that these electrons, when they get energized, come off in some quantized energy levels based on the energy that the electrons, the energy of the light, or the wavelength and frequency of the light that was involved. Okay, and we have also refined, and we teach you how to do electron configurations, and we say there's 2 electrons in the first shell and there's 2 electrons in the second S level, and you can use the off-bar filling rules. But the question is, how do you know that? How do you know where they are and how many are where? So we're going to talk a little bit about that, because it's pretty abstract and you just kind of take our word for it. But we also know that as we look at the electron configurations that there are some exceptions. But if we can't see even the atom, never mind the electrons, how do we know that these exceptions exist or that these general rules are even followed? So the way that we know about the Bohr atom, or that electrons are generally located at different energy levels, is based on the emission spectrum, and we can energize an electron. And once that electron is energized, we can measure, when it falls back, the energy of the electron coming off, and make the assumption that the energy in which it came off must be the energy of that electron. And we can actually measure that energy. Okay, we don't have you do this anymore. Actually, 2 years ago, the students had to do that for the AP exam. Okay, so we've also talked some about ionization energy, which sometimes is called the binding energy, which is the energy required to remove an electron. And we talk about the trends of ionization energy. But where does this data come from? Okay, so here's a table of ionization energies, and we can, you've tried to analyze things like this. But let's take a minute and just look at what this is telling us. So if I take magnesium, for instance, and I wanted to know how much energy is required to make the magnesium ion, what I see is that the energy to require one electron is here, but the second electron's energy goes up. And what you'll see for all of these is there's a certain amount of energy to remove the first electron, but it always takes more energy to remove the second electrons. These are not total energy, but these are discrete. So first electron is this, plus the energy to remove the second electron is this. So the total energy to remove these electrons is about 2100, and I think these are in microjoules. Okay. Same thing here. Silicon takes more energy to remove the second electron. We also see that as you go, this is the third period. As we go across the third period, the energy to remove those electrons becomes higher. Now we can also look at what happens when we get down to the core electrons. In this case, we remove one electron off of sodium. When we're down to the core electrons, we've removed a shell. Same with the magnesium. All of these, the pink represents the core electrons. Significant amount of energy to remove those electrons. So how do we probe further into the atom? Well, we do know the relationship energy is Planck's constant times the frequency. And we know the energy and frequency of different types of electromagnetic radiation. So for instance, if we wanted to remove electrons, valence electrons, that we can actually see in the visible range, it takes between 0.2 and 0.3 megajoules. Megajoules meaning a million joules, right? There are also some transitions that we can't see that are ultraviolet that take even more. So those are ultraviolet transitions. But if we wanted to take off a core electron, let's say, not valence anymore, but core electrons, they take a significant amount more energy to remove. So removing a core electron, I'm looking now at more than a megajoule, right? And I can calculate the frequency of that, and if I look at that frequency, that frequency is in the range of X-rays. So in order to remove core electrons, I need the radiation type of X-ray, right? And this leads scientists to what type of equipment is necessary to make this possible. Okay, so removing core electrons, we said is, let's say, the first electron, most core electron is 103 megajoules, and we can do that with X-ray. But if we can do that with X-ray, we can remove all of them with X-ray. It just takes less of it, right? Less energy. Okay. So any frequency of light that's sufficient to remove the first electron is also capable of removing the others. But we also know that since the outer electrons take less energy to remove than the core, that when they come off, they'll come off with more energy, right? They'll have greater kinetic energy when they come off. So this is a diagram of an actual photoelectron spectroscopy. It's a pretty big unit and it looks a little bit confusing. But this is where the sample is analyzed. And this big machine is where the electrons, as they come off, travel through to identify what energy they have, so we can identify where they must be located. Okay? So that's where they're analyzed. This is where they travel. So this is basically how it works. So let's say I have a sample that I have put into the PES, and the sample surface is exposed. We take light, electromagnetic light that comes in, and this is in the form of X-rays, and hits this surface, causing electrons to be energized. And as they are energized, they get ejected, right? Just like Bohr's model. And as they get ejected, what happens when they come off, this is the part where they go into the detector, and based on the angle at which they come off at, you can interpret or predict the relative kinetic energies. And this is sort of a diagram of what's going to happen. So as I start this animation, I want you to watch what happens with electrons. This would be a lithium atom. It's got 2 core electrons and 1 valence electron. So imagine if we take the X-ray source and we struck this sample that has a sheet of lithium atoms. Watch what happens in the speed, potential kinetic energy of the electrons that come off. And actually also watch what happens to those electrons. Where do they go? So there's a core electron, and when that happens, I see a little peak, right? Some of these electrons, when they come off, they don't go into the analyzer, they go into an atom in front of it, which is exactly what happens to this analyzer. So here I've taken a core electron, and what I see happening is that peak gets bigger. Now I've taken a valence electron. Whoops, that was also a core. Here goes a valence electron, and when I do that, this peak goes up. And you keep doing this until you've collected enough data where the data stabilizes, and then you take a look at your peaks. Okay, so let's say we have a boron atom. We can do the same thing. We can look at the core electrons, we form a peak, right, and collect enough data, and then we can compare borons to lithiums. And when we do that, we see a different energy profile. The hardest to remove electrons, this is megajoules, is much greater for boron than it is for lithium. So let's look at analyzing some data. So here we have a PES graph. Now, there are different ways of showing this graph. In some cases, the x-axis is the megajoules, or the energy required to remove the electron, and the y-axis is the relative number of electrons. But sometimes this is reversed, so the binding energy is on the left, or the y-axis, and the relative number is on the right. What looks a little bit odd about this graph is that the high binding energy is towards the left and the low is towards the right, which is the opposite of what you expect. Normally the 0 is going to be over here, but sometimes you do see it where this is 0 and this is higher. The reason they show this graph with the high energy on the left is because these represent the electrons closest to the positive nucleus. And that's typically how students are going to think about the atom. But if you have a PES to analyze, you have to get your bearings straight. The first thing you have to do is look at your binding energy or ionization energy scale and make sure you know where your highest energy is, and that's where you're gonna have your core electrons. Okay. All right. So the electrons are going to be most difficult to remove. The highest energy are going to be those 1s electrons. Okay. And then if I look at these 2 other peaks, I'm going to have, must be 2s, and if I look at the height, this is 2 bars high, and this is 6 bars high, so there must be twice as many electrons. Those are going to be my 2p electrons, 2 here and 6 here. So we can ask ourselves, what element is this going to represent? And because there's 2 here and 2 here, that's 4, plus 6 here, that's going to be 10, and that's going to be neon. So we can use PES to identify what an atom is. We can also use a PES knowing that this is neon and identifying where are those electrons located. So we know neon has the configuration that we teach you because the PES data tells us that. Alright, so let's identify the element here in its electron configuration. So the highest peak is going to be the 1s, so it would be 1s. 2s, 3 times higher, that must be a 2p with 6 electrons. 3s, 3p. The 3s, the s's all have 2, this would only have 1, so that's going to be a 3p1. And the element that ends with 3p1 is aluminum. So let's take a look. Our choice is there, so this is going to be aluminum. Okay. Alright, so which element could be represented by this spectrum? So I want you to pause and see if you can identify them. Okay, so let's take a look. If this is the highest energy, this is going to be my 2s, this is going to be my 1s, my 2s, my 2p. This is 1, 2, 3, 4 bars, so that's 2 electrons. Another 2 bars is going to mean a third electron. So I have 3 plus 2 is 5 plus 2 is 7. And that's going to be a nitrogen. Alright, so let's see if we can understand which of the following best explains the relative position and intensity of the 2x peaks between lithium and beryllium. So lithium is atomic number 3 and beryllium is atomic number 4. Lithium has 1 valence electron, beryllium has 2. But here we're talking about a 2s peak, right? So we're not talking about the core electrons, we're talking about the valence electrons. So which of these sentences could explain why we see the differences in the peak? So go ahead and pause and see if you can answer this. Okay, so welcome back. So let's take a look at the first answer. It says beryllium has a greater nuclear charge, which is true, than lithium, and 2 more electrons in the 2s orbital. So that would make sense. A greater nuclear charge, which means it's going to be greater attraction to the protons in the nucleus, and it's twice the height, which means is consistent with the fact that lithium has 2 more s orbitals. Let's take a look at the other choices and see if they made sense. B says beryllium has greater electron to electron repulsion than lithium electrons. Well, greater electron repulsions is going to cause the binding energy to go down and not to go up. So this is inconsistent with the graph. C, lithium has greater pull from the nucleus of the 2s electrons, so they are harder to remove. Well, that's not true because lithium's binding energy here is less. It's not consistent with the data. And then D is lithium has greater electron shielding by the 1s, so the 2s electrons are easier to remove. And that is not true either because the shielding for both lithium and beryllium is about the same. The shielding comes from the inner core electrons, and they both have the same inner core electrons, so that would not be true. Alright, let's take a look at question 3. I'd like you to answer that. Pause it, and then come on back. Okay, welcome back. So given the photoelectron spectra for the phosphorus and sulfur, which of the best explains why the 2p for S is further to the left or higher in energy? Okay. But the 3p peak is to the right or lower in energy. So let's look at our options. S has a greater effective nuclear charge than P. That would be true. And the 3p sublevel in sulfur has greater electron repulsion than in P. So that seems to make sense, right? It has greater electron effective nuclear charge, which make the binding energy greater for sulfur, especially in the 2s and the 2p. And the 3p sublevel in S has greater electron repulsions, and if it does have greater electron repulsions, that would make the 3p be less. So that one seems to make sense. Let's take a look at the others. For B, sulfur has a greater effective nuclear charge than phosphorus. That's true, we just said that. And the 3p sublevel is more heavily shielded in S than in P. That would not be true because the shielding in both S and P are the same. They both have the same core. C has a greater number of electrons than S does, which is true. So the third energy level is further from the nucleus. And that is not true. They are both in the same energy level, which makes them about the same distance from the nucleus. D, S has a greater number of electrons than P, which we said is true. So the Coulombic attractions between the electron cloud and the nucleus is greater in S than in P. Well, while that makes sense, it does not explain why the 3p peak is less energy in S. It's inconsistent with the data. So the answer here is A. Alright. So looking at the complete spectra for sodium and potassium, which of the following would best explain the relative positioning of the 3s electrons? So here we'd have 1s, 2s, 2p, 3s. So let me blow this up first so we can see it better. Alright, so let's take a look. Go ahead and pause and then come back. Okay, welcome back. Whoops, gave you the answer. Okay. So the first choice says K has a greater nuclear charge than sodium, and that's true. You know, remember, K is the first element in period 4, whereas sodium is the first element in period 3. Okay, and so that would be true. We'll give it higher binding energy, which is it has. B is K has more electron repulsions than sodium, and that would not be true because they both have one electron in their valence shell, so the electron repulsions would be about the same. Well, there would be no repulsion because they only have one electron. C, sodium has one valence electron in the 3s sublevel. Okay, sodium has one in the, so that explains the height, but it does not explain the binding energy difference. In that sodium has less electron shielding than potassium. That would be true, but if it had less shielding, then it would be stronger, but it's not. So the answer is A. Alright, so let's take a look at the signal intensity. And the signal intensity is the height here, which is an indication of the number of electrons. Which of the following would best explain the signal intensity for the 3s electrons? Well, if you look at sodium, it's got ends in a 3s1, but potassium has a third shell full, and it starts at the fourth shell. So there are 2 electrons here, which is why it has 2 electrons. So this is not because, if we're just looking at the signal intensity, it's not because of the greater nuclear charge, it's not because of repulsion, and it is because sodium has one valence electron, so it would be C. Okay, and sometimes you'll see this where it shows a break here because the energy differences are so great, just to show that there's a break in the x-axis. So, given the photoelectron spectrum of scandium, which of the following best explains why scandium commonly makes a 3+ ion as opposed to a 2+? So let's get our bearings. This would be, 1s, 2s, 2p, 3s, 3p, 4s, 4p. So if it's making a 3+, it's going to lose 3 electrons. So they lose these 2 plus this one. So let's look at our choices. A says we remove 3 electrons, releases more energy than removing 2 electrons. That's true, but it doesn't explain why. Alright, B, scandium is in group 3 and the atoms only lose the electrons that will result in a noble gas configuration. Well, if that was true, it would become a 2+, not a 3+. C is the amount of energy required to remove an electron from the 3D sublevel is close to that for the 4s sublevel, but significantly more energy is needed to completely remove the 3p. So if we look at that, that makes a lot of sense. The energy level requirement is very similar for the 2 of these. Okay. D is removing 2 electrons alleviates the spin pairing in the 4s sublevel, 1s, 2s, 3s. Removing 2 electrons. That would give us a 2+ ion, not a 3+ ion. So the answer should be C here. Okay. Alright, so here's another example of the kind of thing you might be asked to do, is you might be asked to draw the electron spectrum for magnesium. So pause the podcast and try to do that. Okay, so if I'm going to draw aluminum has 1 more electron than magnesium, so it's got a greater nuclear charge. So I'm going to expect that the core is pulled in tighter, that the second energy level is going to also require more ionization energy to remove those, and that so each of these subshells is going to be at a higher energy, and that there's an extra electron out here representing the 3p electron for aluminum. Okay. So at this point, we should be able to identify, translate between the representations of all of these representations of magnesium. Here's a picture of the magnesium atom. Here's Bohr's model. Now we also have this interpretation of where the electrons are placed, and this interpretation that sort of explains why we have this interpretation. Okay. So, you know, the Thomson model helped us figure out that electrons exist in the atom, that there's particles smaller than the atom itself. Rutherford helped us understand that we had a nucleus of a strong, positively charged, dense type, that we have energy, that each electron must be at discrete energy levels, consistent with those that we see in the emission spectrum of atoms. And now we have PES, that tells us about specific energy level, ionization energy level, energy required to remove electrons, and what it takes to remove those. And from that we can get our ionization energy. Okay, that's going to do it for us.